Today our topic is Raoult's law. In Raoult's law, we discuss the cases of binary solutions. Binary solutions containing a solvent and a solute. Here we have two cases. The first case is a volatile solute dissolved in a volatile solvent. What is meant by volatile? Evaporating. That is the meaning. A volatile solvent dissolves, a volatile solute dissolves in a volatile solvent. And the second case, a non-volatile solute dissolves in a volatile solvent. So here two components, you can see two components, black and red. Red is more, so it is the solvent, and black is the solute. The first case, only the solvent, and the second case, the solvent and solute are volatile. Here you can see the combination of two. When there are solute molecules, that will be present in the vapor state. When there are solvent only solvent molecules will be present in the vapor state. You can see it here. If there is solute in the solution, that solute molecules are present in the vapor state. If there is no solute, there may not be any solute in the vapor state, only solvent molecules will be present there. So here we have to analyze these two cases, and now we are going to discuss the first case, a binary solution containing two volatile components. Solute is volatile and solvent also volatile. In such a case, when solute and solvent are volatile, as it is shown in the figure GF, you can see the solvent molecules and solute molecules are present in the vapor state. And what will be the amount of solvent and solute in the vapor state? What is the factor which is affecting the amount of solute and solvent in the vapor state? Surely that will be the concentration. What is the concentration of the solute? That is deciding the amount of solute present in the vapor state. And the concentration is expressed in terms of mole fraction. If there are two components in the vapor state, surely there will be partial pressure. Since it is vapor pressure, we can say partial vapor pressure. So partial vapor pressure of a component is directly proportional to mole fraction of that component in the solution. That is Raoult's law. What is Raoult's law? Vapor pressure, partial vapor pressure of a component in a solution is directly proportional to mole fraction of that component in the solution. Partial vapor pressure is directly proportional to mole fraction of that component in the solution. So what is the statement of Raoult's law? Raoult's law states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. So for component 1, P1, partial vapor pressure of component 1, P1 is proportional to X1. X1 is the mole fraction of component 1. Or we can write P1 is equal to P1 0 X1. Here P1 0 is vapor pressure of pure component. What is meant by vapor pressure of pure component? If that component alone is present, that means we are not mixing it with any other. For example, if you are taking water, it has a particular vapor pressure. And when you mix the water with another component, surely the vapor pressure of water will change. That is the vapor pressure of solution. And if you are taking water alone, that is the vapor pressure of the pure component. So when you take the solvent alone, it has a particular vapor pressure. That is vapor pressure of pure component. And if you are taking the solute alone, it has a particular vapor pressure. That is the vapor pressure of pure component. So P1 is equal to P10 x1, where P1 is vapor pressure of the component 1. P10 is the vapor pressure of pure component 1, and x1 mole fraction of component 1. And this P10, that is a standard value. At a particular temperature, it will be a constant, P10. And when we consider the component 2, P2 is proportional to x2. x2 is the mole fraction of component 2. P2 is proportional to x2, and x2 is the mole fraction of component 2, and P2 is the vapor pressure of component 2. P2 is equal to P20 x2. Here P20 is the vapor pressure of pure component 2. So from this we can say the total vapor pressure of the solution, P total, is equal to P1 plus P2. What is P1? P10 x1 plus P20 x2. So that is another statement of Raoult's law. P total is equal to P10 x1 plus P20 x2. Another statement, P1 is equal to P10 x1. Another statement, P2 is equal to P20 x2. So Raoult's law has different statements, mathematical expressions. Now another expression of Raoult's law. P total is equal to P1 plus P2. Substituting values of P1 and P2, we get P total is equal to x1 P10 plus x2 P20. But we know in a binary solution x1 plus x2 is equal to 1. So what is x1? It is 1 minus x2. Substitute it. 1 minus x2 into P10 plus x2 into P20. Then P10 minus x2 P10 plus x2 P20. If you take x2 outside, P10 plus P20 minus P10. So from this we can conclude it into 2 points. The first one is total vapor pressure over the solution can be related to the mole fraction of any one component. So total vapor pressure can be related to mole fraction of any one component. If you think with your common sense, you can understand it. The concentration of solute is more, surely the vapor pressure of solute will be more. And at the same time, vapor pressure of solvent will decrease. And as the concentration increases, mole fraction of solute also increases. Similar the case of solvent. If the concentration of solvent is more, its vapor pressure will be more. And as the concentration of solvent increases, vapor pressure of solvent increases. And vapor pressure of solute decreases. So it is very clear. Total vapor pressure of the solution can be related to the mole fraction of any one component. And the second point, total vapor pressure over the solution varies linearly with the mole fraction of component 2. That is the equation given here. Total P total is equal to P10 plus P20 minus P10 into x2. x2 is the mole fraction of component 2. So what we can say, total vapor pressure over the solution varies linearly with the mole fraction of component 2. Now what is meant by ideal solutions? The solutions which obey Raoult's law in all the concentrations, that is known as ideal solution. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. What are the characteristics of ideal solutions? It will obey Raoult's law. What is the meaning? P1 is equal to P1 0 into x1, or P2 is equal to P2 0 into x2, or P total is equal to P1 0 x1 plus P2 0 x2. When we mix two liquids, for example, 50 ml component A and 50 ml component B, what should be the total volume? It should be 100 ml. So is there any volume change? No, delta V mixing is equal to 0. Before mixing, total volume 100 ml. After mixing, total volume 100 ml. So initial volume minus final volume is equal to 0. Delta V mix is equal to 0. Similarly, when we mix two components, we are expecting some enthalpy change. Sometimes heat energy may be released, sometimes heat energy may be absorbed. But in this case, in the case of an ideal solution, we are not expecting such an enthalpy change. So for an ideal solution, delta H mix should be equal to 0. Enthalpy change should be equal to 0. When it arises, if the attractive force between component 1 and 1, that means attractive force between solvent molecules is equal to attractive force between solute molecules. That is equal to attractive force between solute and solvent molecules. There is no difference. Interactions between 1 and 1 is equal to 1 and 2, that is equal to 2 and 2. In such a case, you can expect the formation of ideal solutions. But can you identify such a mixture in which all the interactions are same? Solvent-solvent interaction is equal to solute-solvent interaction, which is equal to solute-solute interaction. Very difficult to find out. So we will get some approximate ideal solutions. For example, normal hexane and normal heptane. Normal hexane means 6 carbon atoms in a single chain. Normal hexane. And normal heptane, 7 carbon atoms in a single chain. So you know, in between hexane only van der Waals forces are acting. Heptane also van der Waals forces are acting. And the difference is only in the case of one carbon atom, in the number of one carbon atom. So the attractive force may be almost equal. So it can form an ideal solution. Similarly, bromomethane and chloroethane, their masses are almost equal. Bromomethane and chloroethane. Benzene and toluene. Benzene, you know, there is only the difference of one carbon atom. Toluene and benzene. Toluene has SH3 group attached to a benzene ring. So in such cases, we can expect ideal behavior. Graphically, the ideal behavior can be represented as given here. In the y-axis, vapor pressure is plotted, and in the x-axis, mole fraction is plotted. Here you listen. In this corner, here in this origin, there is only solvent. X1 is equal to 1, therefore X2 is equal to 0. Only the solvent is present. At this state, what is the vapor pressure? It is the vapor pressure of pure component 1 or solvent. Now slowly we are adding the component 2. Then what happens? When we add component 2, the mole fraction of component 1 will decrease. If there is a decrease in mole fraction of component 1, there will be a corresponding decrease in the vapor pressure of component 1. So that will decrease as the concentration of component 2 increases, and finally it will reach a value 0. What is the situation? There are only one component, that is component 2 is present. The concentration of first component 1 will become 0. Then its partial pressure is 0. So here it is the vapor pressure curve of component 1. It is a straight line, you can see it. So here, as the concentration of X1 decreases, vapor pressure also decreases, and when its concentration becomes 0, vapor pressure also becomes 0. And here in this case, X1 is equal to 0 and X2 is equal to 1. Therefore, the vapor pressure corresponding is the vapor pressure of the pure component 2, P02. And here we are adding a small amount of component A. And as the concentration of A increases, its vapor pressure decreases. Vapor pressure finally reaches a value 0, where the concentration also equal to 0. So here, this representation X1 is equal to 0, X2 is equal to 0, and here X1 is equal to 0 and X2 is equal to 1. Vapor pressure, and here the straight line graphs, all these are very important. And what is the total vapor pressure? That is changing from P10 to P20. That also a straight line. P total is equal to P1 plus P2. This represents ideal solutions. Ideal solutions. So this graph is very important when you are asked to describe ideal solutions. You have to draw this graph with all the things given here. Now the case of non-ideal solutions. There are two types of non-ideal solutions. Non-ideal solutions with the positive deviation. In the case of non-ideal solution with the positive deviation, it will not obey Raoult's law. The Raoult's law will be like this. P1 is greater than P10 X1. P2 is greater than P20 X2. Therefore, what will be total vapor pressure? P total. P total will be greater than P10 X1 plus P20 X2. In positive deviation, when you mix the two liquids, its volume should be more than the initial volume. So if you are mixing 50 ml A and 50 ml B, the mixture will be slightly more than 100 ml. So final volume minus initial volume will be positive. Delta B mix should be positive. Similarly, when we mix the two components, the enthalpy change will be positive. What is the meaning of enthalpy change is positive? It will absorb a little amount of energy, heat energy, in order to keep the other component with it. So when it arises, if the interaction between, or the attractive force between 1 and 1, that is greater than attractive force between 1 and 2. So attractive force between 1 and 1 is greater than attractive force between 1 and 2. Similarly, attractive force between 2 and 2 is greater than attractive force between 1 and 2. That means the interactions, attractive interactions less in the case of component 1 and component 2. Solvent-solvent interactions more than solute-solvent interaction. Similarly, solute-solute interaction more than solute-solvent interaction. In such case, delta H mix will be positive, delta V mix will be positive, greater than 0 means positive. Such a solution is showing positive deviation from ideal behavior. Example, mixture of phenol and aniline. In this case, phenol, which can form hydrogen bond between phenol molecules. Similarly, aniline can form hydrogen bond between aniline molecule. So when you mix aniline with the phenol or phenol with aniline, what happens? The hydrogen, it has to break the hydrogen bond between phenol molecules and has to form a new hydrogen bond between aniline and phenol. That is a weaker hydrogen bond. Therefore, attractive interaction is less. Another example, carbon disulfide and acetone. Acetone is polar, so there is some attractive interaction between acetone molecules. But in the case of carbon disulfide, non-polar, so when you mix carbon disulfide and acetone, the attractive interactions between acetone molecules will be affected, or that will be decreased. These are examples, and it also can be represented graphically. You can see it here, a positive deviation here. The graph is as it is explained in the case of ideal behavior. Here the dotted line represents ideal behavior, and in the case of positive deviation, you can see a positive curve. In the case of P1, positive curve in the case of P2, and a positive curve in the case of total vapor pressure. And what is next? Non-ideal solutions with negative deviation. Now everything is clear to you. Total vapor pressure will be less than P10x1 plus P20x2, or P1 will be less than P10x1, P2 will be less than P20x2, delta H mixing will be less than 0, means negative, delta V mixing will be less than 0, means negative, and the intermolecular force will be, attractive force between 1 and 1 is less than 1 and 2, which is greater than 2 and 2. That means molecular interactions, attractive interactions between 1 and 2 is greater than that between 1 and 1 and 2 and 2. And here the examples are ethanol and acetone. Another example, chloroform and acetone. Chloroform, which cannot form hydrogen bond between chloroform molecules. And in the case of chloroform, the attractive interactions weaker than that between chloroform and acetone. For negative deviation, another example is nitric acid and water. Another example. When nitric acid dissolves in water, you know, large amount of heat energy will be liberated. Delta H mixing will be negative. It's a graph. The dotted line represents ideal behavior, and here you can see total vapor pressure, which is shown by a negative curve. There also a negative curve. Okay, I think it is enough for today, and asuetrophs that we can see in another class. Okay, goodbye.